When a crack appears on the surface of a concrete building, we usually think that is the moment the damage begins. But in a coastal environment, a physical crack is often just the final chapter of a story that has been quietly unfolding for years. Salt from the ocean does not need a storm to destroy a wall. It only needs to find a pathway small enough to remain completely invisible to the human eye. This is a story about the hidden vulnerability inside modern coastal infrastructure. It is a forensic investigation into a phenomenon commonly referred to by the media as concrete cancer, though engineers know it by a much more precise name. We are looking at chloride-induced corrosion. For a city like Dubai, built on the promise of flawless luxury and relentless growth, this chemical process creates an unprecedented challenge. A metropolis built by the sea must constantly defend itself against the very environment that surrounds it. If the defense fails, the consequences move rapidly from a structural nuisance to a massive economic burden. Why does a material that looks as solid as a rock allow salt to pass right through it? The answer changes how we understand the true cost of building a city in the sand. If you walk past a coastal structure and look closely at the surface, you might notice a very specific type of damage. On the surface, it is just a thin, jagged line. But the direction of this crack is not random. It almost perfectly mirrors the exact location of the steel reinforcement bar buried deep beneath the surface. Sometimes, this crack is accompanied by a faint reddish-brown stain bleeding through the gray material. If a structural engineer taps this area with a specialized hammer, they will not hear the sharp, clear ring of solid stone. They will hear a dull, hollow thud. That hollow sound is the echo of a separation happening in the dark. When people see these defects, they often jump to simple conclusions. They blame the natural settlement of the foundation. They assume the extreme desert heat caused the building materials to expand and contract too quickly. But forensic engineering tells a completely different story. The damage we are looking at was not caused by the earth shifting below, nor by the sun beating down from above. The destruction was entirely internal. It was generated by a slow, silent buildup of pressure radiating from the steel core outwards. The term concrete cancer is not a scientific classification. It is a journalistic metaphor used to describe a localized degradation that spreads and worsens if left untreated. The real culprit is a chemical mechanism driven by the presence of chloride ions. These ions arrive daily, carried by the gentle sea breeze, settling onto the pristine facades of luxury hotels and high-end residential towers. If modern building codes are fully aware of this exact risk, how does the salt actually bypass the solid exterior? To understand the vulnerability, we have to shrink down and look at the material on a microscopic level. We tend to look at a concrete wall and see a single, impenetrable barrier. But concrete is not a solid sheet of glass. It is actually a highly complex, microscopic maze. It is composed of large pieces of rock and sand, all bound together by a cement matrix. Within that matrix exists a sprawling network of microscopic pores and tiny capillary channels. These channels act exactly like tiny straws. When the surface becomes wet from humidity, morning dew, or splashing waves, these tiny channels actively suck the moisture inward. The Arabian Gulf provides one of the most aggressive environments in the world for this specific process. The seawater here has an exceptionally high concentration of salt. The air is heavily laden with marine aerosols. These microscopic droplets of salt water drift inland, coating every balcony, every exposed column, and every parking garage entrance. Once the chloride ions dissolve in surface moisture, they begin to travel through the porous maze of the concrete. They move through capillary absorption and chemical diffusion. Any microscopic cracks left over from the original curing process simply provide a fast track for these ions to travel deeper. The level of danger depends heavily on where the structure is located. Elements submerged completely underwater actually face less risk because oxygen cannot easily reach the steel. The most dangerous zones are the splash zones and the atmospheric zones, where structures undergo continuous cycles of getting wet and drying out. Each time the surface dries, the water evaporates, but the salt is left behind. Over months and years, The concentration of chloride inside the concrete slowly builds up. It pushes deeper and deeper, millimeter by millimeter, entirely hidden from the view of tourists and residents. If the surface remains perfectly dry and beautiful, is the steel underneath truly safe? The answer is complicated, because the steel possesses a hidden defense mechanism of its own. The steel reinforcement bars are not simply hiding behind a physical wall of stone. They are actively protected by an invisible chemical armor. When cement mixes with water during the construction phase, the resulting chemical reaction creates a highly alkaline environment. The internal pH level of healthy concrete is incredibly high, usually sitting between 12.5 and 13.5. In this highly alkaline environment, a microscopic oxide film naturally forms across the entire surface of the steel. Engineers call this the passivation layer. As long as this passivation layer remains intact, the steel simply cannot rust, even if moisture and oxygen are present. The concrete cover is providing a chemical sanctuary for the structural skeleton. This is the primary reason why we can build enormous skyscrapers near the ocean in the first place. But this invisible armor is not invincible. The chloride ions that have been slowly migrating through the pores are naturally drawn toward the steel. For a long time, nothing happens. This is known as the initiation phase. It can last for 5, 10, or even 20 years, depending on the thickness and quality of the concrete cover. During this entire period, the building looks structurally flawless. There are no cracks. There are no rust stains. The physical asset appears to be performing perfectly. But eventually, the concentration of chloride ions accumulating at the surface of the steel reaches a critical tipping point. Engineers refer to this as the chloride threshold. The moment this threshold is crossed, the highly alkaline environment is neutralized at the local level. The microscopic passivation layer is instantly destroyed. The chemical sanctuary is breached. The steel is now exposed and vulnerable in a dark, damp environment. This marks the end of the initiation phase and the beginning of the propagation phase. What happens next is a slow-motion mechanical disaster that completely changes the structural integrity of the building. The moment the passivation layer collapses, an electrochemical reaction begins. The steel reinforcement bar essentially becomes a battery. Different parts of the steel act as anodes and cathodes. Iron atoms lose electrons and dissolve into the surrounding moisture. They react with oxygen and water to form iron oxide. We know this common material simply as rust. But in the confined space of a structural column, rust is not just a cosmetic problem. It is a profound physical threat. The byproduct of this corrosion process occupies significantly more volume than the original steel. Depending on the specific type of iron oxide formed, the rust can take up to 6 times as much physical space as the metal it replaced. The steel bar is effectively trying to grow in size while being tightly clamped inside a solid block of stone. This expansion generates an immense outward pressure against the surrounding concrete. Concrete is incredibly strong when you push down on it, which is why it can support the weight of a 100-story tower. But it is notoriously weak in tension, meaning it breaks easily when you try to pull it apart or push it outward from the inside. As the rust continues to accumulate, the tensile stress builds up until it exceeds the tensile strength of the concrete. The material has no choice but to tear itself apart to relieve the pressure. A microscopic fracture develops internally and slowly propagates toward the exterior surface. When the fracture finally reaches the outside air, a visible crack appears on the facade. The steel is literally pushing the concrete out of its way. If the corrosion continues unchecked, the cracks widen until entire chunks of the concrete cover break off entirely. This event is known as spalling. The rusted steel skeleton is suddenly exposed to the open air. From the moment that first visible crack appears, the building has inadvertently opened the door for a secondary wave of attacks. We have now entered a self-accelerating feedback loop. Before the crack appeared, the chloride ions had to slowly navigate the microscopic maze of pores to reach the steel. It was a difficult, time-consuming journey. But the new crack creates a massive, unobstructed superhighway leading straight into the heart of the structure. Water, oxygen, and fresh salt can now pour directly into the core without any resistance. This sudden influx of elements dramatically accelerates the corrosion rate. More rust is produced, creating even more outward pressure. This causes the existing cracks to grow wider and longer, which in turn allows even more water and salt to enter. The degradation feeds on itself. The structural element is now trapped in a rapid downward spiral. This is not a theoretical model. It is a daily reality for thousands of exposed elements across coastal cities. Let us look at a typical luxury balcony facing the sea. When it is newly built, it represents the ultimate premium real estate feature. But it is also fully exposed to marine aerosols every single day. The morning condensation wets the surface. The intense afternoon sun dries it out, leaving the salt trapped in the pores. Over a decade, the chloride slowly crosses the threshold. The steel begins to rust. The underside of the balcony develops a hairline fracture. Water from sudden rainstorms seeps into the fracture. Eventually, a heavy piece of the balcony ceiling detaches and falls. This exact cycle does not only happen on balconies. It targets the edges of floor slabs. It attacks the support columns in underground parking garages where salty water drips from car tires. It silently targets the areas hidden behind expensive decorative cladding. Are the most dangerous locations the ones directly facing the ocean, or the hidden corners where water and salt get trapped and are rarely inspected? This physical breakdown forces us to look beyond chemistry. At this exact moment, the story transitions from a fascinating scientific reaction into a highly complex financial crisis. When a structural element begins to spall, it instantly becomes a massive asset management problem. This is where the physical reality of concrete cancer collides directly with the economic engine of Dubai. The city has built its global reputation on the promise of flawless, futuristic luxury. The tourism industry here does not sell a basic travel experience. It sells an aesthetic illusion of absolute perfection. Hotels in this region demand some of the highest average daily rates in the world. To justify those premium prices, the visual environment must remain absolutely pristine. A tourist paying $1,000 a night for a premium suite will not accept a balcony with cracked concrete or rust stains. But repairing chloride-induced damage is not as simple as applying a fresh coat of paint. It requires a heavy, disruptive, and incredibly noisy construction process. Workers must erect scaffolding. They must use jackhammers to remove all the contaminated concrete surrounding the rusted steel. The noise of concrete chipping travels easily through the entire structural frame of a hotel. You cannot quietly drill concrete while guests are trying to relax by the pool or sleep in their rooms. To perform these repairs properly, hotel operators are often forced to shut down entire wings or block off premium facilities for months. This leads to a direct loss of revenue. The true cost of a coastal building is never just the money spent to construct it. The hidden cost is the massive maintenance debt required to constantly defend it against the environment. In a booming tourism market with high occupancy rates, closing rooms for structural repair creates immense economic friction. But ignoring the problem is not an option. If the repairs are delayed, the corrosion spreads, and the eventual intervention becomes exponentially more expensive. Real estate investors rely on predictable rental yields. But when a residential tower requires a multi-million-dollar concrete rehabilitation project 10 years ahead of schedule, those yields evaporate. The sinking funds collected from property owners are often completely insufficient to cover the staggering cost of deep structural repairs. The marketing brochures focus on the spectacular skyline and the endless summer, but the engineering reality is a constant, grinding battle against degradation. How can a city relying on perfect aesthetics manage a disease that remains invisible right up until the moment it destroys the facade? Discovering chloride corrosion before it causes spalling is essentially a hunt for a ghost. Engineers cannot wait for the concrete to crack, because by that time, the repair costs have already multiplied. They must conduct forensic investigations on structures that appear entirely healthy to the naked eye. The first step is a simple visual observation, searching for faint rust stains or tiny signs of moisture ingress. The second step is a delamination survey. Technicians meticulously drag heavy chains across parking garage floors or tap structural columns with specialized tools. They are listening for that hollow acoustic anomaly that indicates the concrete has already separated from the steel internally. But the most critical investigations require looking deep inside the chemical makeup of the wall. Specialists perform electrochemical assessments. They use advanced equipment to map the half-cell potential of the structural surface. This technology can identify areas where the electrochemical activity of the steel is abnormally high, pointing to active corrosion even under a flawless surface. To understand exactly how far the enemy has advanced, engineers must physically drill cylindrical core samples out of the building. These heavy stone cores are sent to a laboratory. Technicians grind the concrete into fine dust at different depth intervals. They perform chemical titrations to measure the exact percentage of chloride present at every single millimeter. They are not just asking if salt is present. They are asking exactly how many millimeters the salt is away from touching the steel reinforcement. This creates a highly counterintuitive reality for building owners. A perfectly smooth, beautifully painted column might actually require immediate, expensive intervention because the lab results show the chloride is dangerously close to the steel. Meanwhile, a visible crack elsewhere might just be a harmless shrinkage issue. If you are a property manager with a limited budget, do you spend your money repairing a crack everyone can see, or do you spend it extracting invisible salt from a wall that looks perfectly fine? Early detection gives you choices. Late detection leaves you with massive bills and angry tenants. If the Arabian Gulf is such an aggressive environment, why do engineers continue to build reinforced concrete structures right on the water? The answer is that the engineering community is fully aware of the threat. They have developed a formidable arsenal of defensive technologies to fight back. Building in this environment is entirely possible, but it requires accepting that survival is an active, ongoing process. The first line of defense is the concrete mix itself. Modern high-performance concrete is designed with a very low water-to-cement ratio. Specialized additives like silica fume or fly ash are mixed in to make the microscopic pore network incredibly dense and difficult to navigate. Engineers mandate much thicker layers of concrete cover to ensure the salt has a longer distance to travel before reaching the steel. The steel itself can be upgraded. In highly exposed zones, developers can use epoxy-coated rebar, which adds a physical plastic barrier over the metal. For the most critical infrastructure, they can use stainless steel reinforcement, though this increases the construction budget dramatically. Chemical corrosion inhibitors can be added to the liquid concrete mix. These chemicals delay the breakdown of the passivation layer even when chloride arrives. For existing buildings that are already contaminated, engineers can deploy the ultimate weapon known as cathodic protection. They install a permanent network of titanium mesh or discrete anodes directly into the concrete. They run a constant, low-voltage electrical current through the structure. This impressed current forces the steel to remain in a cathodic state, physically preventing the iron atoms from dissolving into rust, even if the concrete is heavily saturated with salt. Engineering is not helpless against the ocean. The existence of these advanced defense mechanisms proves that the threat is understood and can be managed. But every single one of these solutions comes with a catch. They demand precise execution during construction. They require constant monitoring. And most importantly, they cost a tremendous amount of money. None of these technological marvels grant a building permanent immunity. They do not eliminate the risk. They simply buy the city more time. The ongoing battle against chloride corrosion exposes a fundamental illusion about modern urban development. We are culturally conditioned to believe that once a skyscraper is topped out and the ribbon is cut, the project is finished. But in a hot, humid, and salt-heavy environment, a building is never truly finished. It simply transitions from the phase of construction into the phase of endless defense. The narrative of Dubai is often framed around the triumph of human engineering over a hostile desert. The marketing campaigns sell a frozen moment of perfection. They promise a resilient utopia where the elements have been permanently conquered. But the reality of forensic engineering tells us that nature does not surrender. The ocean does not stop generating aerosols. The humidity does not stop driving moisture into the concrete pores. The chemical laws of thermodynamics dictate that refined steel desperately wants to return to its natural state as iron ore. The alarming part of this story is not that concrete cancer exists. Engineers have known about it for decades, and they possess the tools to control it. The true vulnerability lies in the vast gap between the rigorous timeline of material degradation and the short-term expectations of investors. People want to buy a luxury asset and forget about it. They want to believe the beautiful facade represents permanent structural health. But the physical reality of the Arabian Gulf demands extreme vigilance. It requires property owners to proactively hunt for microscopic damage and spend millions on preventative maintenance while the building still looks perfect. When the economic pressure mounts, when hotel occupancies fluctuate, and when real estate yields tighten, the maintenance budget is usually the first thing to be delayed. And delay is exactly what the chloride is waiting for. The sea does not need to destroy a building in a single dramatic storm. It is incredibly patient. It only needs to deliver tiny, invisible grains of salt to the surface, day after day, year after year. Engineering can slow this process down significantly. Careful inspection can detect it before it becomes catastrophic. Proper funding and maintenance can control the damage and keep the structure entirely safe. But absolutely nothing can make the battle disappear. The true price of a coastal metropolis is not the billions of dollars required to build it in the first place. The real cost is the unbroken, expensive commitment to protect the hidden steel that no one will ever see, for as long as the city stands. If you found this forensic dive into the hidden mechanisms of urban infrastructure valuable, please consider subscribing. We will continue to look past the marketing brochures to explore the real forces shaping our world. The most important warning signs are rarely found where the advertisements tell you to look. This video examines documented mechanisms of chloride-induced corrosion and the regional durability challenges associated with coastal environments. It does not claim that every building in Dubai is damaged, failing, or structurally unsafe. The conditions of specific buildings vary drastically according to their unique design, material quality, exposure levels, construction standards, and ongoing maintenance practices. This content is an analysis of structural mechanics and urban economic pressures based on publicly available engineering principles. It does not constitute financial, investment, or professional engineering advice.